right. Welcome to our fourth and final keynote of ALT. So I'm very happy that we have and that I have the opportunity to introduce Vitaly Feldman. Vitaly got his PhD at Harvard, spent several years as a research scientist at IBM Almaden, and has been at Apple for a long time now. And Vitaly has done sort of amazing work on really beautiful and elegant theoretical problems, ranging from kind of classical computational complexity of learning to work in differential privacy, to work in something called adaptive data analysis, all of which I've really enjoyed and been inspired by. And today is going to talk about another very exciting and inspiring line of work on memorization and machine learning. So welcome, Vitaly.
Hello. Yes, thank you, John, for a very kind introduction and unusually serious coming from you. It's a great pleasure to be here and an honor to speak at ALT. I'll be talking about a sequence of work on the role of memorization of learning, trying to kind of provide some theoretical understanding of memorization. And this understanding will rely on two main parts. So one is the properties of the data, and the second is data processing. Data processing is, of course, a very important part of machine learning pipelines, and I will tell you how we, at Apple, we create a Python library for training and for data processing that runs efficiently both on Apple Silicon and on CUDA NVIDIA architectures. Just kidding, data processing will be inequalities. Anyway, and they will be strong. Well, assuming that my clicker works. If it doesn't, it will be just regular data processing inequality. Anyway, so let me start with a little bit of by describing some of the empirical phenomena that we'll be trying, that are motivating this work and we'll be trying to understand. The first one, sort of maybe not commonly thought of as memorization. I typically refer to it as label memorization. And this is a very famous phenomenon in this community that starting from this 2013 of introduction of AlexNet, the state-of-the-art machine learning algorithm that relies typically on neural networks, eagerly fit the training data. And what that looks like is the training accuracy is typically very high, close to 100%. And at the same time, test accuracy, especially on the harder data set, is much lower, maybe in 20 to 80%. And that suggests that some of these labels, since they're in the training data set, are memorized because the model is not that great, but it fits pretty much all the labels. This phenomenon is has been made both more famous and more clear through this, again, very famous work on rethinking generalization by Zhang and others. Again, you all know about it, but briefly to remind you is that it shows that, so in the top of this table, it shows that the training on the regular ImageNet label, where you show that the training accuracies that is being achieved is 92%, then there is a very high test accuracy of about 78%. But a very similar training accuracy would be achieved even on completely random labels. And of course, in order to fit completely random labels, they don't have a pattern. You have to memorize them. And of course, in this case, the test accuracy is completely close to zero. So this is the first phenomenon we'd like to understand. And the second one, as perhaps have been described somewhat more recently, is data memorization. And again, this phenomenon has been made famous through this work of Carlini and others, who show that if you put a somewhat carefully chosen prompt into a GPT-2 model, it will start spitting parts of the training data. In this particular case, some address of some employee, which is probably potentially sensitive. And since then, this is maybe like an ancient model by today's standards, but they have also introduced this, reproduced this experiment on the production ChatGPT-3 model in 2023. Again, with a cleverly selected prompt, they got the model to spit out parts of the training data. And there's a lot of weird stuff about this phenomenon, but the one we are being interested in, that it clearly shows that the model contains training data. By the way, of course, feel free to stop me and ask questions as usual. So, and these phenomena are not exclusive to LLMs and text. They have been also shown in, by Carlini and others, Somepali and others in the context of image generating models such as stable diffusion. With a bit of prompting, careful prompting and filtering, you can get them to reproduce near exact replicas of images contained in the training data set. So, and one can also say maybe potentially it's just like some corner cases that very clever security researchers were able to pinpoint. But actually, some of the same teams have shown that this data memorization happens at very large scale. For example, they measured the percentage of memorized tokens or long token sequences for many of the open source models at different parameter sizes. And this is the percentage of the tokens that are of the total tokens that is being memorized. And for larger models that have more parameters, this percentage is typically between 0.5% and 1% of training data, and it's typically larger for larger models. They also showed on some specific architecture that as you increase the size of the model, the percentage of the data increases. So the larger the model is, the more of its training data it memorizes, and it's typically in the range of 1%, which, given the scale of these data sets, is a massive amount of data that is being memorized. So the reason why these phenomena attract, there are many reasons they attract a lot of attention, but one of the clear reasons is that memorization in some contexts can be harmful. One sort of obvious context like this is privacy. Even label memorization can lead to so-called membership inference, being able to infer whether a certain data point is in the data set or not. And of course, if the if the model is trained on some sensitive data, then extraction of that sensitive data would be a significant privacy violation. Another context where memorization is considered potentially harmful is copyright violations, because a lot of copyrighted work are being used for training. And this is also not a sort of hypothetical concern. Has been recently shown by Fedor Cooper and others that from an open source Llama 70B model, relatively small by today's standard model, you can extract nearly verbatim copies of the Harry Potter book 1 and the 1984. Yes, right.
I have a question. How do you define memorization? And I mean,
that's the talk is for you. These are empirical phenomena. We'll get to it. We'll get to some definitions. Don't worry. So we will talk about specific definitions both for data memorization and label memorization. So so this brings me to the goal of this work, is kind of understanding these memorization phenomena. And the specific question that I'll be focusing on is the question, is memorization necessary? And concretely, let's say we have an algorithm that achieves a certain level of performance, or optimal performance is achieved by some algorithm that does appear to memorize. Can the same performance be achieved without memorization? Again, we'll have to define things, but that is the type of the question I would like to answer. And the reason I'm interested in this is the interesting question in my mind, is that of course it's crucial for being able to mitigate this phenomena, if to understand whether it's necessary or not. And I believe it's also kind of fundamental for machine learning itself, and to the best of my knowledge is not answered by sort of either classical theories or maybe some of the other recent advancements. And before going into sort of the story of answering this question, let me also mention a question that we are not going to try to address, and that's the question of why memorization does not harm generalization, that has certainly occupied some of the community. And the reason why I think that's this question will not help us understand this memorization phenomena is that this view that first of all, we know that while memorization is a symptom of overfitting, it does not mean that it causes it, or that these two have to be necessarily coupled. In fact, this view that the model sort of ability to overfit is tightly coupled to its ability to memorize is based on these kinds of the way I think of it is models that have limited expressivity and only one knob that controls the model complexity. And for such models, basically, the fit is kind of tightly linked to the model's ability to memorize. But in today's models, they have hundreds, if not thousands, of different knobs, and you can easily, and they're expressive enough to be able to both memorize as much as they want, while also having the best fit that they need to the best generalization. And everything is, of course, tuned to as well as we can to fit as well as possible. And hopefully, at least somewhat, this is somewhat controversial. I'm happy to talk about this. Anyway, that's the introductory part of the talk. Let me just give you a very brief roadmap for the talk. So this was the motivating phenomenon. I'll start by talking about this simpler phenomenon of label memorization. I'll actually go, instead of talking about maybe empirical intuition, I'll give you a little bit of theoretical intuition of what might be going on. I'll then describe very briefly an experimental validation of some of the ideas that come out of this theory. And then I'll talk about the data memorization, the models, and the results we can prove for this model. And I'll also hopefully will have a bit of time to tell you about the techniques we use, which are these strong data processing inequalities. So let's get started on this label memorization. And of course, the first thing we need is a definition. And we'll define, and again, the goal is to capture memorization of just the labels in the data. And the definition will be the following. It will be per a certain score, which we'll measure per data set, which you'll think of as consisting of n labeled examples, x, y, 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 and a specific example in the data set, which we'll just we'll refer to using an index. And of course, it will be per learning algorithm A. We'll say that a certain algorithm that example I is memorized with this score. The score is defined as the difference between two values. The first value is just the probability that the model output of the algorithm it agrees with the example that it has seen. That's just empirical accuracy on that particular example, minus the probability that the same model trained without that example will agree with this example. And the reason it's probability because everything is randomized. And the intuition here is that if the model predicts that example correctly, if there is a big improvement in the accuracy as a result of seeing just that example, is that this label is likely memorized. Just it is a definition, not necessarily the most comprehensive one, but it does have some nice properties. First of all, the notion itself should remind to many of you the sort of the kind of leave one out stability. And it also is related to differential privacy, but it's you could say a lower bound on differential privacy. But it is to learning theorists, you should remind leave one out stability before differential privacy. So I don't know what happens to Shai. So actually, like some classical results in learning theory is that if you measure this notion, if you average it over the data set and average over a randomly chosen sample data set, then in expectation it's equal to basically the generalization error, or to the expectation of the difference between generalization error, I think, and the empirical error, which is sometimes referred to as generalization gap. So in some sense, this memorization, the overall memorization by dataset is essentially equivalent, at least in expectation, equivalent to having this generalization gap. So if there is a large generalization gap, say a constant generalization gap, then it means that for a constant fraction of examples, this score is at least a constant, which indicates a big improvement in accuracy, which we think of as being memorized. Okay, so now we have a definition. We can start asking the question that we are interested in, and we'll start with an extremely simple learning problem, which I'll refer to as unstructured prediction. And again, the goal here is to distill the phenomena to the sort of the simplest learning setup you can imagine, maybe not the most natural one, but the simplest that I can think of. And in this setup, we'll have some domain, which has completely no structure, but we'll think of it as just m numbers from 1 to m, and they'll be labeled by, they'll have binary labels attached to them. The distribution over X, this domain will be completely unknown. And there will be some, the labeling function, which will be fixed, will be completely unknown. Just think of it as being completely unpredictable. and we'll be given a data set S of n ID labeled examples. So now that's a learning problem, maybe, again, not the most natural one. There seems to be no pattern, but maybe there is a pattern, you just can't discover it given the number of examples you have. So it is a well-defined prediction problem. So let's say you observe some data set. Here is a data set, some numbers, some of them labeled, then not so clear what you can do with it. Everything, there is no structure. You can, for example, at least notice that some of the examples are repeated. Well, some of them occur once, some occur twice, and some occur four times. It's not really clear what you can do besides basically just memorizing what you have seen. And indeed, it's not hard to show that for any marginal distribution, sort of the best hypothesis you can produce, minimax optimal hypothesis, given for sort of no assumptions on the function, unknown function, is to just memorize the data sets. Well, basically the hypothesis will say that if you get an X, output the labels that you have observed. If you have observed its label, otherwise output a random label. Hopefully it makes sense. Let's quickly look at the properties of this algorithm. First of all, its empirical error is 0. It's perfect, fits the data perfectly. Its generalization error, I happen to know the distribution is, well, 26%. It's actually not such a bad algorithm. It's much better than random guessing that you would get otherwise, and something that one could use if one actually had to predict, do some prediction in this setting. And we can also notice that it actually, that according to this definition of label memorization, it memorizes all the examples that occur once in the data set. So all those are memorized just because the prediction changes as whenever you observe that example. That should be clear. So now we have an optimal algorithm that memorizes actually a very large fraction of a data set. And the question is that, can the same performance be achieved without memorization? Is that memorization necessary? And if you think for a little bit, it's really not such a hard problem to analyze. You can prove something along the following lines, that whenever you don't memorize these singleton examples that you need to memorize to fit, you'll be just losing their whatever the drop in accuracy you'll experience is the true probability mass of all those examples. So you'll get some theorem along these lines. We'll denote the set of all the examples you observe once by this S times 1. Then every algorithm is suboptimal relative to this optimal algorithm by the fraction of this singleton that doesn't memorize, which, well, we can measure it as a fraction, times the total marginal probability of set of the things you observed once, times the half, which is the improvement in accuracy you get from each. Should be clear result. So now the question whether memorization is necessary really boils down to what is the marginal probability of all the things that you observed once. If it's tiny, then maybe you don't care. And this really just then becomes, well, so this question we can formulate a little bit more clearly. We want to know what is the expected probability mass of things you'll observe once when you sample from distribution. It has a formula. It doesn't, not so important what it is. It's if you actually think a little bit about it, it is equal to the total probability mass in your distribution. So this is just we're thinking of these are our elements, and that's their probabilities. And the expected mass of all the singletons is equal roughly to the total probability mass in your distribution of frequencies which are on the order of 1 over n. It's some kind of kernel, but anyway, it's roughly this part of the distribution. So now the question is this part of the distribution significant? And it, of course, depends on what kind of distribution you care about. Some people like uniform distributions. We can try to ask practitioners what kind of distributions do they care about. And a lot of them will tell you that there's a standard folklore that the natural data distributions are so-called long-tailed. And what they usually informally mean by this is that things that are kind of relatively rare, infrequent, make up a significant fraction of the data set. That's sort of what they informally mean. If you ask them to pinpoint some specific distribution, they'll talk about power law distributions, and maybe most famously, zip distribution, where the whatever the frequency of the ith most frequent element. Scales is with 1 over I, famously followed by the words in many languages, and so on and so forth. It's we can measure this weight of that probability, this part of the distribution for this for zip. Of course, it depends on the support. So for a support of size m, the weight of this fraction of the distribution is roughly 1 over log m. So if m is not that much larger than, say, n, this will be a relatively significant part of the distribution. And importantly, for all n, it doesn't even kind of matter what n is. Matters, but not hugely. So that's example. So the answer to the question about memorization is in the properties of this distribution. Of course, it's we just had an extremely simple setup. There was no noise. Of course, you will memorize if there is noise. It's great to memorize. But let's for a second think what happens if you do have noise. And I don't want to get into complicated noise models. So let's start with the random, our favorite type of noise. Just flip the label with some probability 1/4. And let's do it to our data set. That's the version, the same one. We just flip each label with probability 1/4 independently. So, well, the singletons still have their some kind of labels. The ones which you observe more than once, sometimes the labels change. As you observe, still very easy to analyze. If you think for a second, what is the optimal algorithm in this case, is to predict the majority of the, well, look at all the examples with the, for that number and predict the majority label. And it's still, still memorizes all the singletons as defined, because the majority is exactly just that single label. And it actually still useful strategy. In fact, memorizing the label of that example will still, in expectation, improves the prediction accuracy on that example by 1/4, because random label is more likely to be correct than incorrect. So it's a good strategy. And in fact, exactly the same proof still goes through the memorization. Every algorithm will still be suboptimal by whatever this memorization factor times the frequency of all the singletons, with only the changes that now that it will be scaled by 1/4 instead of 1/2. That's the improvement in accuracy. And more generally, the sort of the conclusion, even from this noisy setup, is that memorization is necessary for near optimal accuracy as long as it improves prediction accuracy on singletons. So other models can be fit into this scenario. So as long as this phenomenon of, okay, single example improves accuracy on that on some part of the distribution, then memorization will be necessary. Now let's try to map it to something which looks a little more realistic. And the mapping will rely on this notion of subpopulations or clusters in distribution. And what are those? And the sort of basic at a high level, this idea of that the distribution may have clusters comes from the sort of observation, often empirical, is that the data distributions are not just homogeneous blobs like a single Gaussian. They have some data points which are similar to each other, others which are much maybe quite different from each other. So informally, I'll think of a subpopulation or a cluster as a subset of the domain that contains elements that are more similar to each other than the rest of the population. And it may be useful to think of something of taking a look at some images, for example, of birds in the C100 data set. And you can notice that they come from like hundreds of bird species. Many of the shots are taken across many different backgrounds, different bird parts, magnifications, a lot of differences. And some of these images are quite obviously closer to each other than to others. There's a huge variety. There are many, many different subpopulations of examples. So basically, the way the sort of this more discrete setting is mapped to this maybe more natural setting is that each point now corresponds to an entire subpopulation. And the reason, well, sort of the property that allows us to kind of map from one to the setting to the other is that these subpopulations are sufficiently distinct from each subpopulation, rare subpopulation is sufficiently distinct from other examples, so that before observing an example, the accuracy maybe is not very high. And once you observe even a single example, your accuracy grows noticeably on the entire subpopulation. So it's a reasonable property, natural, hopefully relatively natural one, but it's one that one can actually try and verify empirically. And that's the next thing I wanted to tell you about, the experimental validation, which we did with John Zhang. And here the goal is specifically to see whether memorization improves accuracy on subpopulation as well as we can. So first of all, we start with, in order to understand whether memorization improves something, we need to estimate these memorization scores. The original ones that cannot be, it's too computationally intensive to estimate it. We estimated a smoothed version of those. I don't quite have time to talk about it right now, but just as a sanity check, here are some examples of this memorization score measured on the ImageNet bobsled class. These are bobsleds that are memorized by the standard, I think, Inception architecture. These are all memorization score of around 1. If you look carefully, actually, 3 middle ones are not bobsleds. The left and right are actually bobsleds, but very weird, strange images. They're all memorized in the sense that the label is fit, but only after observing. And it all is fully consistent with what we expect to happen theoretically. And just for comparison, here are some bobsleds that are not memorized. They're, as you can see, very prototypical and easily recognizable as bobsleds. So now we would like to see what kind of, we would like to test whether the memorization of images like this improves accuracy on the respective subpopulation. Of course, we don't have access to the actual subpopulation, but we do have a test set, and it might have some, it's a relatively large test set, it will have some examples from the subpopulation. So we expect to see maybe 1, maximum 2 other examples from the same subpopulation, which really gain or benefit from memorizing these examples. So how do we measure this benefit? We just also look at the difference between the, so we look at this influence notion. It's kind of similar to a standard notion of influence. It's an influence of example I on the accuracy on this example XY. So we look at the difference in the prediction accuracy on some pair XY when we between the sort of the full model and the model without that example. It just measures the how much benefit memorizing that label or entire example can give. So we have measured it across many data sets. Let me just show you one example, and examples from other data sets are very much consistent with this. So just to quickly explain what we are seeing here. So in the left column, we are seeing some example from the training set. And it's on top of it, there is its memorization score. It's all memorized, so memorization scores are all high. On the right side, we see example from the trainings, from the test set that that sort of most benefit from memorizing the example. On the left side, ordered by the benefit they get. So, and on the top, you get the benefit, they improve in the accuracy. So it's extremely, like it's very high for that barrel, but it's so if you look carefully, you will, my summary, at least of what's happening, is you'll see one example which has a significant benefit. And visually, it's extremely similar. So in some cases, it's actually probably from the same set of images. So that's not surprising. But in other sets, it's actually a different image, but it's similarly, clearly very related. And all the other examples, this benefit is small. In fact, it's just selection bias. You can basically, there's for all we can say for all of the other ones, it's not a significant benefit. And that's really, at least in my mind, kind of exactly what one expects to happen. We memorize these examples because they have a clear, they give us clear improvement on similar examples in the test data set. And this is not, again, just a couple of examples. It's actually a randomly selected sample from about 3% of the image test set examples that are benefiting from this kind of memorization. It's a significant enough effect for people to optimize for. And maybe I should also mention it's not just for images. That's since been reproduced on text data set by my collaborator Zhang and others. So that's all that I wanted to say about the label memorization and the empirical Phenomenal. Let me now talk a little bit about the data memorization. And again, we'll start with some definitions. So, and just very briefly remind a bit of notation. Okay, maybe I should stop for a second. Any questions so far? Yes. Yes. Here or further? This one?
Yeah, exactly. So you're saying there's benefit of memorization because you can predict better on the test set. Right?
Yes.
But you're not optimizing to predict better on the test set.
Well, no, you're optimizing to predict better on the test set. Not this particular one, but in general, that is what we're optimizing. We're optimizing for generalization performance. There's a separate validation set on which we optimize everything for. I mean,
so are these actually the validation set?
No, this is test set. This is train set, test set. There's typically also, everything is optimized for the generalization performance in the sense that people train and improve their networks to do as well as possible on the test set, right? I mean, the optimization itself, of course, doesn't see the test points, but it explains, but we tune the algorithm to, in this case, to memorize, and the whole point is that's what memorization gives us. Of course, I'm happy to chat later. Yes, Tim. Fair point. These kinds of techniques of looking what's memorized always identify all these kinds of data set issues. So these are the ones, if you have a duplicate, it will have the highest improvement, and it's a kind of hard to predict one, the one that is actually memorized. That will, these techniques immediately find those and actually have been used to detect various issues in the data set. But not all, if you look carefully, there are lots of cases where it's completely normal behavior. These are, okay, this is whatever, this coffee pot. These are clearly different coffee pots. It's just their similar style. And here is this a different carpenter set if you look carefully, but just their similar presentation style. So I think it's just like the nature is. There are some things that look similar, even though they come from different places. Yes. Just for that which alone, because when you train it without that. Let me mention there are a lot of works that try to look at mechanistic aspects of memorization, where it happens, which layers are more responsible. I haven't maybe done. There's some part of it in my work, but maybe it's a longer discussion that we'll have offline. All right. All right. Let's go to data memorization. The definition, just briefly, slight change of, not change of notation, but update to the notation. Will be referring to our data distribution by P. Our data set is still S, but now it doesn't have to be labeled, although it will be labeled, but we'll just refer to Z1 for Zn. It's ID data set. And we have A is the learning algorithm, and A of S is the model produced by this algorithm. These are, note that this the data set is a random variable, and the learning algorithm is a random algorithm on a acting on a random variable is a random variable. So the definition we'll use, and it was first introduced in the work of Brown, Ban, Smith, Talvar, and myself, is the good old notion of mutual information due to Shannon. And specifically, it's a definition for parameterized by the number of examples that you have observed, the data distribution from which you're sampling the data set and the algorithm. It's just the mutual information between the data and the model. Basically, how many in expectation, how many bits in expectation the model contains that are specific to the data set. And why I'm saying specific to the data set, because the distribution P is fixed here. There's no information about the distribution P. It's just specific to the data set, and that's the one way in which it's different from the maybe older definitions of that use memorization in learning. We're only per data set. And maybe also worth to mention, because we're talking about memorization, is that this notion of memorization does not kind of explicitly imply any sort of extraction attack. It just tells you there will be information about the data set, where it is, how much it is not entirely clear, but it's information specific to the data set. And if there is a lot of it, I would trust security researchers to find some of it. Anyway, so while let me also briefly mention that while maybe its application and specifically to measure this irrelevant or excess memorization is new, the notion itself has been studied in a few works in learning theory. Maybe most famously through it has been used to prove generalization bounds. It's known that low mutual information of this type implies generalization. It was first done in a work of Dwork, Roth, Pitasi, and Reingold, where we used a stronger notion of mutual information referred to as max information. It has led to the work of Rousseau and Zhu, who used specifically mutual information to derive generalization bound, and a long sequence of follow-up works. And more recently, even stronger notions have been used, such as conditional mutual information that many of you are probably familiar with. There have been also a few lower bounds proved on this notion in our community. For example, in the context of pack learning, Basili and others, and Livni and Morant showed that a lower bound specifically for learning, I believe, a threshold. Again, the notion for this notion information, the lower bounds roughly log d, where d is the description length in this case of example. So it's maybe too weak to explain any of these phenomena, and the problem is not exactly the type of problems we'll be interested in. And the second, maybe more relevant work is a much stronger lower bound of omega d for d-dimensional mean estimation and all problems that involve implicitly this d-dimensional mean estimation. Again, the difference here is that these problems involve estimating basically d-independent parameters. So the fact that you need to memorize d bits is a little less surprising in this case, and doesn't directly apply to our prediction-like problems that we're interested in. So that's what I wanted to say. So let me tell you about the kind of problems we'll be analyzing using this definition. And these are, I refer to them as cluster classification problem. Here again, the goal is to kind of look at the simplest possible problems that distills the phenomena we're interested in. So all problems will have the following general shape. They'll live in d dimensions, and the goal will be to classify a point as either coming from some cluster distribution, p theta, parameterized by parameter theta, or some fixed null distribution, p0. Maybe as an example, think of two Gaussian. The positive examples will be coming where p theta are the sample from some Gaussian around the parameter theta, and the null distribution is the Gaussian around the origin. And that's the goal, is to classify into this problem. It's an easy problem. In fact, the way we'll set up okay, so maybe it's easy, but not too easy. You need at least one example to be able to solve this problem. Maybe the interesting, maybe just I also should note it, but we only care about positive examples here, because then from the null we can generate them ourselves anyway. So we need at least one positive example of a cluster. And in fact, once you observe the parameters will be such that this easily separatable. Once you observe a single example, you can have very high accuracy. Think of 99%. Well, this algorithm will achieve the easiest way to achieve, at least, will be actually just do a nearest neighbor. When you observe the next one, check whether it was close to that example or not. Or you can also do a linear classifier, but in any case, you will need to fully memorize that example to be able to run that algorithm. So you'll have an algorithm that achieves very high accuracy, relies on memorization. And the question, is it test memorization necessary? That's exactly what we'll try to answer. And before going towards actually answering and stating these results formally, let me just give you a couple more definitions. So we'll be looking at average case problems. And here, average case has two nice properties. One is it makes our lower bound stronger, and we'll be proving lower bounds on memorization. And secondly, it makes the sort of the language of information theory a little easier to describe. So specifically, we'll have for this, as I mentioned, we'll have cluster distribution will be parameterized with this theta, but we'll also have this meta distribution over parameters. We'll call it phi. Now once we have the distribution over parameters, we can measure the expected memorization. What is the average memorization, which is just the expectation of the memorization for a specific parameter distribution when you sample the parameter here. And that's in the language information theory, is just the conditional mutual information between the data set and the model, condition on sort of knowing this theta. And it's equivalent to just looking at all the information contained in the model about the data set and the parameter and subtracting the information about the parameter. Simple enough. And also, of course, we will be talking about in this case, we'll talk about average error, which is just the expectation of the error when you, of an algorithm when you look at sample the parameter. Okay, now we can start defining specific problems. The first one will be the Gaussian cluster identification problem. It's an instance of this type of clustering problems. Now the parameter itself will be chosen itself from the Gaussian distribution with a zero mean and identity covariance. And the p theta distribution will be again a Gaussian with around this parameter theta just scaled by some lambda, which is a scalar I'll define in a second, and roughly the same covariance. It's not so important, slightly smaller. So again, just to remind you, the goal is to classify as coming either null or this p theta distribution itself a Gaussian. So it's easy to see that if you set this lambda parameter scale to be roughly d to the -1/4, the problem becomes easy, solvable with a single example. So now the question, can you do it? Well, do you have to memorize? And the first result I would like to tell you about is with from a joint work with Guy Kornowski here and Xin Liu, is that any algorithm which has kind of non-trivial accuracy on this problem will have memorization, will need to memorize this number of bits that scales as d over n. So if you observe relatively few examples, it's like order 1 example, the number of bits you will need to memorize is order d, essentially the constant fraction of the information in the vector that you have, ignoring some quantization issues. Yeah, so that's a trade. Well, this basically what we get is that first of all, you need to memorize a lot when you have few examples. It also explains that you need to memorize less as you observe more examples. In fact, per example, you memorize even less. Like the memorization kind of decays quite fast. We also show that that kind of matching upper bounds. These are up to log factors, and in fact, there is the algorithms are relatively simple. Basically, you either do this kind of linear. Once you have a single example, you can't do much. You just use the nearest neighbor. Once you have a bunch of examples, you first take the mean of them, and then you can either project that to a lower dimension. And remember, in the lower dimension, that will work. And another way, actually a more elegant way that was communicated to us by Tor Latimore, is that actually you can add Gaussian noise to the mean, and it will also erase information in a kind of in the optimal way. It again will be a long description, but informationally it will have the right trade-off to give the matching upper bound. So in that work, we also give these kind of trade-offs for other examples of clusters. So another one is this Boolean clustering problem, which is very similar to Gaussian, except now the null is the uniform distribution of the Boolean hypercube, and p theta is kind of a distribution which is biased toward theta with this lambda bias. The trade-off looks similar, except at square root d there, it drops the theta becomes identifiable, and you don't need to memorize anything about the data. It's another nice phenomenon. This is more maybe like a classical regime of learning. You don't need to know anything about the data. You know the hypothesis perfectly. And then yet another example, which actually problem comes from an earlier work, which I mentioned with Van Braun and others, is we call this sparse Boolean clusters. A similar problem where, again, null is the uniform distribution and p theta is uniform over points that satisfy some fixed square root d conjunction of roughly square root d literals in it. So there the trade-off is even sharper. It starts as d but then it decays as d over 4n, and around log d, things become identifiable, and no memorization is necessary. Anyway, that's all that I want to say about the results. Let me tell you a little bit about techniques. These are based on SDPIs. And let me first remind you what the regular data processing inequalities are, and I hope it's not entirely useless. But if everybody knows and everybody says don't mention, we'll go ahead. Anyway, what are the data processing inequalities? It's just this basic property of this notion of mutual information that if we have a, it's usually referred as Markov chain, or just basically 3 jointly distributed random variables such that the last one, z, depends on x only through y. So only information that z has on the first random variables comes through y, which kind of, again, just language of random variables just means that z is condition is independent from x conditioned on y. So in this setting, this step of processing from x to y is known because to lose information, or actually never gain any information, which translates into this standard data processing inequality that the mutual information between x and z is at most mutual information between y and z. Makes sense? We'll be interested in the strong version of it. That is, parameterized by parameter alpha, and it's we'll talk about this. We'll talk about specific pair of random variables x and y satisfying this alpha SDPI. If for all y z's, which kind of post-process y, with this basically with this property, we have that mutual information that x has on z is at most an alpha fraction. Alpha is less than 1 of the mutual information that y has on z. And again, informally, the point is that this step from x to z kind of loses information contained in x. Maybe if a concrete example would be a pair of 2 Boolean random variables, where one is sort of a noisy version of the other, or they're just then the noisy version of the variable will lose information contained in the first one. So this pair will satisfy this alpha SDPI, and the same is known in the world of Gaussian. If for two correlated Gaussians, this processing step loses information. So what does it all have to do with learning? So let's look, and it's actually a pretty simple connection. Let's just first lay out all the random variables that we have in this setup. We'll have our data distribution is the first random variable. The second random variable, generally distributed, is the training data set sampled from this p theta, the distribution determined by the parameter. The third one, we output a model, is another generally distributed random variable. And finally, we want to evaluate the model. We need to draw a fresh sample, in this case, from the same cluster, p theta. And we would like to apply SDPI. So first of all, we already know that one part of the chain is here. We know that model depends on all the other random variables only through the training data set, right? That's the only thing it sees. That's the only way it depends on the other parameters. And the other thing we sort of, now what we'll look at this part of this pair of random variable. And the reason why we look at those is that, first of all, we can observe that if the model has non-trivial accuracy, then it has to have some information about the test example. It has to have some information, mutual information with the test example. Otherwise, if they're independent, you cannot hope to predict whether the example is comes from the same cluster or not. So for non-trivial accuracy, need at least some constant number of information. Now, if this pair of random variables satisfies an SDPI, alpha SDPI, then automatically this means that, by the time you observe this information in the data set, a lot of it has been erased. So if if this is an alpha SDPI, then the information that the model has about this data set is at least 1 over alpha of the information about the test point, which is just 1 over alpha. It almost seems like we're almost done, except here we have measured this notion measures all the information and includes also information about the parameter. So we need to do the conditioning step or removal of the information about the parameter. And And very nicely, this can be done just using another SDPI. So we'll now look at this pair of random variables. So if this processing step from the parameter to a data set generated from this parameter itself loses information, for example, it satisfies gamma SDPI, then we can say that the information that the model has about the parameter is the gamma fraction of the overall information it has. We can remove that gamma fraction. It's all super simple, like all one-line things. Then the conditional mutual information, well, after removing that information about the parameter, is just 1 minus gamma divided by alpha. So here is the lower bound we want. It's just a function of two parameters, alpha and gamma. We need to estimate it. Now, if you set things up correctly in this setting, then for some settings, you'll almost immediately get our result. Specifically, the setting that you can derive just from almost immediately is the, let's say, a Gaussian where you observe only a single example. Then everything is just, this is a sample from a Gaussian, this is a sample from a single Gaussian, and this is a sample from a, you can just apply standard things, get the lower bound we claim. Things are a little more complicated when you have an entire data set. It's just SDPIs are tricky to prove. People don't prove them for data sets. So what we do to get this, we have an extra argument we call SDPI via domination. We introduce some extra random variables, which we call dominating test sample, dominating train set. There are random variables which are structurally much simpler. Just think of it as being also sampled from just a simple distribution, but they can be post-processed into entire data set and contains all the information that is contained in the data set. So now if one proves the SDPI between, one can, maybe we use kind of standard SDPI for these dominated random variables. From those, one can derive SDPI that we're actually interested in. There are some complications as usual. These are all approximate, and the approximation is not so easy to deal with, but in the end, it all kind of works out roughly as we claim. Okay, that's all that I want to say about the techniques. Let me, yeah, any questions so far? Yes. So these are distributions over clusters. In a second, we'll connect those to zip. Now, there are no frequencies. A single cluster, and from something like a high-dimensional distribution, it's like a Gaussian or Boolean hypercube. Actually, next thing we're going to do is connect them back to zip. Anyway, let's go back to connecting these lower bounds to fitting into the bigger picture. And for this, we'll first need to kind of realize how do we think about the data in the city? Where do we stand now in terms of our data modeling? And well, maybe the first observation that it's kind of useless to think about data in its original representation. But the nice thing about neural networks and LLMs is that they're either implicitly or explicitly optimized for computing semantic data embeddings. What are semantic data embeddings? That are embeddings in which things that are semantically similar are close in some kind of cosine similarity or other Euclidean metric. So we'll think about the data after this embedding. And well, based on the intuition I have described, the data, we should think about data distribution as consisting of clusters or these subpopulations in this embedding. And well, because this semantic, it's natural to think when we are faced with a classification problem is that things that are in the same cluster are likely to be from the same class. So, and maybe now when we have these different clusters, the question is, are they all say have the same frequency? No, we should think of them as having these long tail frequencies. Some clusters are bigger, others are smaller. So we emerge with maybe like a visualization of this kind. You have some different cluster, different variances, different sizes, and they are kind of, this color corresponds roughly to the class. Maybe it's a little harder to think how is it related to LLMs, but actually if you think about an LLM, it's still a predictor of the next token, which is a discrete class based on an embedding of the prefix. So you can think of the LLM data as also living roughly in this world. And maybe even before LLMs, this kind of view is consistent with a lot of the classical methods, whatever. Gaussian mixture model, clustering, nearest neighbor, SVMs, and so on and so forth work because data is somewhat clusterable. So now let's try to connect this kind of general model to maybe a simple synthetic model which combines these ingredients and hopefully prove some lower bounds for this type of model. And we'll refer to this model as multi-class clustering. It's kind of based on the stuff in my earlier work and was more explicitly described in the work I've mentioned. And it's parameterized by the number of clusters M, the distribution, each cluster distribution phi, and some, in addition, some pi, which is a frequency prior, the prior that we believe how frequencies behave. And it works very simple. We will first pick the frequencies that we want. It's just some independently from this prior. We'll normalize them. Then we'll sample the cluster parameters randomly and independently. I just don't know how else to sample things. And then the marginal will adjust the mixture of these clusters with these parameters with the frequencies that we've chosen. And we'll label them randomly by each by its own label. That is less significant choice. We can do other labeling strategies, but for simplicity, let's think of each having a different class. So for this obviously synthetic model, we can prove a lower bound that every algorithm that is close enough to optimal in accuracy will satisfy the following memorization. And sort of the memorization will be sum over all clusters of the memorization per cluster memorization. And that's what sort of the important part here is that when you measure per cluster memorization is the sample complexity that is observed for that clusters. So if a cluster observes one or few examples, then it will be the lower bound that we saw for just a single or several samples, which is, as you remember, is typically D. So basically this means for all things that you observe once, you'll be paying roughly D bits. That's the summary for this synthetic model. That's all that I have to say about the sort of more technical side. Let me conclude, given that I'm also out of time. Well, maybe the basic high level point of this works is that ubiquity of memorization, the fact that we observe this phenomena is explained. It's not a coincidence. It's explained by the properties of the data. I've described some theoretical and quantitative models to kind of look at these phenomena, and hopefully it will be helpful in studying those. Well, and maybe specifically, we have introduced some new technical tools based on SDPIs, but I also hope will be useful. There's quite a bit of sort of interesting implications. One of obviously some are for privacy, and including some obvious ones, and maybe some that still need to be researched. And then maybe for our community, the thing that I think maybe the most important is it points to kind of more faithful learning models, and I kind of described some maybe elements of these more faithful models. I don't know how sort of what is the sort of the ultimate faithful model of learning, and I hope some of you will come up with those. But I do have some maybe points that that these models should not be satisfying, or things that maybe the kind of modeling sins that this community often commits, including myself, and that's why I feel like I can actually call them sins. That if we want our models to be closer to kind of more realistic modern scenarios, we shouldn't be committing any further. So and I'm certainly not the first one to say to point those out, but maybe we can still mention. I think it's worth mentioning them again. The first one is looking at marginal distributions that is completely uncoupled from the labeling functions. Maybe some famous example will either not assume completely anything about the distribution, or assume that it's some kind of Gaussian, but the half space goes right through the center of the Gaussian. It's Shai is laughing, so okay, at least some people, it resonates at least with some of us. As the second one is that the model class choice is completely independent of the data set. There's some model, fixed model, and we run the n to be as long as we like, and we'll just get some rate. The reality is that all models are kind of fit to roughly a certain data set size to be able to memorize. It's basically one of the parameters that one tunes that when selecting a learning algorithm. Is the model basically the model capacity, and it's a function of the data set. And finally, maybe it's not strictly speaking a modeling choice, but kind of approach to analyzing algorithm. If the generation error, sort of our analysis of the performance relies explicitly on the closeness of an empirical estimate to the true population. I think it does teach us something important, and this still plays an important role, but I think maybe that's, again, something that we've done maybe for too long at this point, and we could maybe try to depart from this type of bounds. That's all. Thank you very much for your attention, and let me know if you have any questions.
Time for a couple questions, and then I'll be around for lunch.
Yes, I'm around for lunch and the rest of the conference. And I'm happy to chat. I hope I generate at least some puzzled whatever thoughts, and happy to discuss those. Yes, Lev.
So maybe I can ask about one of the obvious implications for privacy. Noticing the connection to differential privacy. Like on the one hand, we can train neural networks in a differentially private way by perturbing, examples or whatever, the gradients and stochastic gradients. On the other hand, you say that we kind of need to memorize in order to do well. So is there just a trade-off? Is it the case that somehow, can you tell me what the obvious implications are, since I haven't thought of them through?
All right. So empirically, it's well known that there is a penalty for when you train things with differential privacy. They definitely do not memorize, and we definitely observe a penalty in terms of the kind of performance people are able to achieve. So the best accuracy with sort of reasonable privacy parameters is typically, like in terms of the error, is typically several times higher error. So it depends somewhat on the data set. But like it took a while to get to something like 95% on MNIST was a big effort. So empirically, it's a well-known fact, and there are many reasons we sort of, well, there are other evidence we know, okay, from learning that privacy is harder. I think this is like explicitly one of the reasons that explains this empirical difficulties. Differential private algorithms do not memorize all these. If you try to make these measurements on differential private algorithms, you will not get any, you will not be able to extract data, and will not be able to, like, differential privacy works, and it probably suffers from this. It basically confirms this phenomenon. If you don't memorize, you will be suffering. Yeah.
So just to follow up, so that means like the large companies don't use differential private because they just don't work well enough.
It's a trickier. There isn't just an answer like that. It's true that certainly if there was like a cheap and easy way that didn't harm us, then probably people would have used differential privacy. That's maybe one of the reasons. I think the problem is more complicated than just that reason. Yeah, but yes.
Well known that Google and they set the privacy parameters in the use of GPSG values which do not guarantee privacy, only but they empirically seem to give enough privacy. Internally, they treat it as like a.
Yeah.
Then how does that work?
Well. So that's a little bit the space. There is a gap between what we know how to prove about differential privacy and what it actually achieves, and then what is achieved by methods which are kind of have some of the effects of differential privacy, not without necessarily, again, having the provable guarantee. And that's that space. And it's like clipping the gradient is already a both standard part of a differential private training, but it's also used for other reasons, and it's known to reduce these kinds of effects and sometimes even improve performance. So that's maybe the point is that internally there are some privacy-inspired techniques that are used that help reduce memorization, but they're usually not done in a way that is aggressive enough to prevent memorization. Yes, sir.
To me, intuitively, it looks like those definitions are very strict because there's a big gap between having mutual information and being able to recover chapters of Harry Potter. There is, and also I think that to me, differential privacy is a too strict requirement because there is a big gap between on every event the difference of probability is very small. I would be able to get someone's personal data. So are there definitions that are
Mhm.
more close to our intuition of what we mean by privacy violation or rights violations?
Certainly for memorization, and both for privacy and memorization, there are other definitions which are weaker. For example, there are definitions that are based on an extraction attack. For example, one example of this definition is what is the shortest prompt that would allow you to fully elicit a piece of data set, a piece of training data. Like the shorter it is, then the more kind of memorized it is. The issue, okay, I think these are great definitions in sort of and that work empirically. Proving something about these definitions is typically very hard, partly because they can be easily kind of if you look at if you want to prove a lower bound, something that no algorithm can do, you can kind of work around failing these, make sure that these attacks will fail, but the information is still there, and maybe a different attack will extract it. That's kind of the main reason why we work with these information theoretic notions. And the other part of it is just, okay, the big part of the gap is the kind of thing we know how to prove, and that's we only have ourselves to blame for this, versus the thing that maybe are true.
Thanks, Vitaly, again.
All right, thank you.